ISTB presents, in association with Dhanmanjuri Community College, DM University Imphal, launching a series of educational programs, recorded online classes for undergraduate and postgraduate students by teachers from various colleges and universities. During this COVID-19 lockdown, every day on ISTB Nongin, 8 p.m. from 24th May 2020 onwards. What's for Dept? Only on ISTB Nongin.
Okay, coming back to the second part or in continuation of my earlier lecture on hydrogen atom. So this is part 2. Let us see. In our previous lecture, we have solved the equation, angular part of that equation that was called equation 6, and that solution to be given by this spherical harmonics. That is y11 is equal to this one, and that is equation 17. Now, this L is a quantum number. The value of L is 0, 1, 2. How it comes, I'll tell you, though I have written it first. You see that. Please remember what we have learned in my earlier class, that the value of small m can be 0 plus 1 or minus 1 plus minus 2 plus minus 3 and so on. But we are getting a condition here that value of m should be minus L2 plus L. This comes on solving that equation, which we equation 6. From this equation part, the relation between L and M is this one. M is equal to ranges from minus L2 plus L space by every number 1. That's integral space. Okay. So M can be only integers 0 plus minus 1, and that automatically implies that small l should also be numbers, but they cannot be negative integers, simply either 0 or positive integer, which we call it non-negative integers. Okay, L is non-negative integer, where we will later be calling it by azimuthal quantum number or orbital quantum number in hydrogen atom. Now, coming back to the equation 5, that was our radial equation, that was equation 5. In that equation 5, we are going to put the values of V, the potential, and lambda. Lambda is L into L plus 1, please remember. Okay. So after putting it, I get this expression. This is the part where I put the value of V, and that lambda on the right hand side, L into L plus 1, that I am putting it here. Now I am going to rearrange it in this way. You see this, the next part. So this is the second step was after rearranging it. Okay, put it here and divide by this r square. Okay, 1 by r square, divide it. For the first term comes like this, second term, this one, got it. And third term r square, then you group it together. So that is your second part. Now, in the last line, this is the last red one that we are getting it after. Now, you simplified it, and you are taking after the derivatives, you will get this 2 term. So this is the 2 things, first, second, and the rest as it is. Okay. So this is the equation, that previous one, that this previous equation. This equation number 19, again, I am putting it here, just to just will be using it, so I am putting it just like recalling, so I have put inside it box. Now I am putting this capital R to be equal to UR by R. Then I take this derivative d by dr. Then I get this expression, these 2 functions here, so you will get 2 terms here. So that is known to you, taking derivative to functions. So that rule I am applying. Again, you take derivative, second order derivative, then you will get how this one. How many terms? 1, 2, 3, 4. from this another 2, from this another 2, that is 3. Okay, then I need not explain it much. So you simplify this first step, group it, this 2 and this 2 that contains du by dr, du by dr. This 2 you group it, after grouping it you get the second one. So only that thing is done, and that I call it equation number 23. Now using equation 20, 21, 22 in this equation 20, 21, equation number 22 in equation 19. So I get this expression. So using this 20, 21, 22 in 19, I get this equation. We'll see this one. After simplifying it, then I'm taking this second order derivative as it is here, and group this first order derivative du by dr, got it? What we find is that this one, after getting it, and this is plus, they get cancelled. So that term does not contain, that means du by dr get cancelled, minus 2 by r squared du by dr, and here you plus 2 by r, 1 by r. So this is positive sign and this is negative sign, they get cancelled. So only this your terms containing remains, and then second order there. So I group all those terms that depends that contains only on the second part. You see this 1 by r is there. So that can be simplified by multiplying by r here, small r here. Then you get this last equation. That is d square u by dr square plus twice mu by squared square. Same thing here, only this r, they get vanish. Okay. Just for recalling it again, I am writing that's equation number 23. Now we are going to introduce these parameters. Rho is equal to alpha times r, where alpha square is equal to minus I times mu e by I squared square. Then you find this derivative d by dr, it will be equal to alpha times d by dr. Straight away you can get it. Again you do it second order, then you get this equation. So we are going to use this equation 24 and 26 in this equation 23. So after inserting it, I get this expression alpha squared d square u by d rho square plus 2 by mu e by squared square plus this one and this one. In next step, this alpha square is dividing in all terms. So when you divide this, or I can say instead of dividing, multiply by 1 by alpha square. Then that alpha square for the first time get cancelled. Multiplied here, that is why alpha square here, 1 by alpha square. Another here 1 by alpha square, then 1 alpha, then it will be only 1 alpha will remain. And again you multiplied by here. Here I have not cancelled, simply I put alpha square, okay. Now, on further simplification, what we do is that this first term, okay, no change. The second term here, this alpha square value, we know that alpha square value is given by equation 25, which we call it minus I times mu e by I squared square. That value is inserted here. And the whole core things from here, z is twice mu z e square I squared square 4 pi epsilon naught times alpha. That I call it capital A for simplicity. So plus capital A by rho minus, same thing here, alpha square alpha get cancelled, and you get only this term L into L plus 1 divided by rho square. So on simplification, cancel it from here. You after cancel it, you will get it minus 1 by 4. This term no change. Last one no change. That is called equation number 27. So this was our equation 27. Now, in order to solve this equation number 27, we'll examine its asymptotic behavior. That means the behavior of this function in the limits of rho tending to 0 and rho tending to infinity. In the first case, we'll see when rho tends to infinity. So when this term rho tends to infinity, what happens is that you can take it as infinity, a by infinity, okay, 0, minus L into L square by infinity square, that is infinity. So L into L square by infinity. So there will also be 0, 0 here, 0. This one minus 1 by 4, only that remains. So this is the equation we get in the limit of when rho tends to infinity, we get this expression. And this has a solution of the form UR tilde when rho tends to infinity, e to the power plus minus rho by 2. So this is the solution that we are getting it from this part. Now you examine it. The examination is this. We know that the wave the wave function cannot go to infinity. Okay, so if you take plus rho, here I am taking either it will be plus rho by 2 or e to the power minus rho by 2. That is the meaning. So if you take plus rho by 2, here you put infinity, e to the power plus infinity, then it will get infinity. Then the solution diverges. So it is not allowed. So we have to neglect that part and we'll take only minus rho by 2. So e to the power minus rho by 2 is taken, and this is the solution that we have to get it in the limit rho tends to infinity. We are getting this solution UR tilde e to the power minus rho by 2, and that is called equation 828. Next we consider the part rho tends to 0. Okay, so when rho tends to 0, something by 0, like this, something by 0. So this 0, actually it's not 0 but very near to 0. Okay, so this term dominates, others will be very small. This 1 by 4 minus 1 by 4 plus a by rho, they will be very small. Only this term will be very large. So I am counting only this large one, that is d square rho u by d rho square plus minus L into L plus 1 rho square times u r is equal to 0. That I missed it. There should be 1 equal to 0. Sorry for that mistake. So there should be 1 0. Anyway, now the solution will be this one. You are tilde rho to power s. When rho tends in, the solution is this one, rho to power s. Now, using that solution, that previous one, that rho for that this one. Okay, using this in that other one, that's equation 30 in 29. So using that equation 30 and solution 30 in 29, after inserting it, you will get an expression like this: s into s minus 1 times rho s to power s minus 2 minus L into L plus 1 rho to power s minus 2 is equal to 0. And this should be true for all the coefficients. So the only thing we get is that this is possible only when the coefficients vanishes, that is s square minus this one, s into s square minus s, okay, minus L into L, L square minus L equal to 0. So we get this, then this can be rearranged, s plus L times s minus L minus 1, product of two functions is equal to 0. And product of two factors is equal to 0. And this gives either this is equal to 0 or either this is equal to 0. From that, we are getting this equation. When this is 0, s plus L is equal to 0, I get the solution s is equal to minus L. Or when this factor equals 0, I get this expression s is equal to L plus 1. So these are two possible solutions. Out of the solution, we have to see one thing. We know that the solution must be finite when rho tends to 0. This rho tends to 0. So in that earlier equation, rho to the power s. Okay, when you take that, if you take that minus L, rho to the power minus L means that rho will comes down. Then you cannot take that value rho to be 0. Then that value will be infinite if rho tends to 0. We are only left with this option that this s is equal to L plus 1. Again, we check it for this being rho to the power s, rho to the power s, and that when that s is equal to L plus 1 means rho to the power L plus 1, and that will be a finite number. Okay, so we have to accept this as the solution. S is equal to L plus 1 is the solution. Now the earlier equations, the solutions, possible solution for mu r when rho tends to infinity and when rho tends to 0. So counting all those things, we should finally get this expression of the solution for the u to be of this form: e to the power minus rho by 2 times rho L plus 1. Another factor function called L, which is a function of rho, and that function L is expressed in terms series solution. then from k is equal to 0 to infinity ck rho k, where ck is a coefficient. In a series solution we have to assume it. Now let's see, this is equation number 34. Next part, we take this first order derivative with respect to rho. This one you take first order derivative with respect to rho, so you get this one. Here you get 1 factor, 2 factor, 3 factor, so we have to get 1 factor, 2 factor, 3 factor. So this is the thing after taking first order derivative. So again I am writing it, that's first order derivative here. Next, taking this second order derivative, we'll get this total, you see, 1, 2, 3 terms, and each term has factor 1, 2, 3. So total you will get 9 factors. 1 first term, 1, 2, 3. These 3 terms from this derivative of this first term, and this next second 1, 2, 3 from the derivative of this second part, another 3 terms, and from this last one another 3. That is what I get. Okay, now you simplify it, you cancel it, you group it, and you get this expression. One term contains second order derivative with respect to rho, and the other one first order derivative with respect to rho, and the last one no derivative, simply L. Okay, now those values we again I am recalling it. This is the expression for UR, and this is expression for second order derivative. That whole thing I have not written, only this just to recall that idea. Okay, I don't have the space, so I have just put it to recall my previous slide. The previous slide is this one, this one, this value. Okay, that is what I am recalling it here now, and this is equation number 27. Okay, just we are going to use it. Now we are going to use this equation number 33, the expression for u, equation number 36, the expression for second order derivative. In that equation number 27, here is the second order derivative. You are going to put these values, and here you are going to put this value u in that second one. Now on putting it, this is what I get: e to the power minus rho by 2 rho times L plus 1 and so on. Okay, and this is from the second part. This is from the second part. This is from the second part. Here race is the value from the first part. Now we are going to simplify it. After simplifying it, what we get here is this expression: rho times d square L by d rho square plus twice L plus 1 minus rho dl by d rho, and that one that does not contain derivative. So simply, so you just see this one, this first term. Okay, second term no change, first term no change, second term as it is. Third term also, I am after cancelling this one and this one. So finally for the third term, I get this expression after simplification. Okay, and that I call it equation number 37. So this is the equation 37. This equation 37 is same as this associated Laguerre differential equation. You just observe this, they are same, provided this beta equals twice L plus 1. If this beta equals twice L plus 1, this term and this term will be same. Now, and this A this A equals this one, then these two are same, so they are the same associated Laguerre differential equation. Now we know that the solution, the resulting equation has a solution at rho equal to 0. Possible solution which is regular. That means you can it will have the derivative. Okay, that's mean. Now this has a solution which has possible solution including rho equal to 0. The value of this A should be a non-negative integer. Means the value of A can be either 0 or 1 or 2 or 3 and so on. So that value of A, I am calling it n subscript r, and this small n subscript nr is called radial quantum number. So we are writing it again here instead of this A, I'm putting it NR. It's equal to A minus L minus 1, and you bring that A to this right side and NR to other side, you get that one. Okay, and this sum depends on this. These are all numbers. Just recall it. L was also numbers, non-negative numbers. Okay, so all are numbers. NR is also number. So it will simply be a number, and by convention we are putting this capital A. Let us call it small n. That is the meaning. Okay, and later on that small n will be known as principal quantum number. Okay, so this small n will be called principal quantum number. So these are the values L, possible values from 0, 1, 2, 3 up to a maximum number of n. And this you can know it from this expression. We know that this n is fixed. Okay, so if nr is the small, the value of this nr is the minimum, this will be maximum. So minimum value is 0. When you put 0, L will be equal to this one. You go to the other side, L will equal to n minus 1. That's why it will, L value will be 0, 1, 2, 3 up to n minus 1. Now the value of n, capital A, which we used earlier, I'm just putting it, recalling back. Here I'm going to put this small capital A by small n. Okay, so after putting it, you get this. Now you square it both sides. Square it this left side, right side. Left side squaring, right side squaring. You get this, and after this you will just see this. There will be one alpha square. Okay, that alpha square value I'm putting it here. Now on simplifying it, we get this expression for energy E. Here that E, I have used this, that capital E denoted, being denoted by En, because it is going to be depend on that small n. So I have changed the symbol capital E to small n. So subscript En is equal to minus mu z e square e to the power 4 32 pi square epsilon naught square I square by n square. It depends on n square. So you see this one. This is the required energy eigenvalue for that hydrogen atom. So you just see that the energy expression depends mainly, forgetting about this constants. You see that it depends on n square. That means those which have the same number of same n, though they may be having different values of L and M, but they are having same principal quantum number n, then their energy will be same. That is called meaning of degenerate. States having same energy. So the energy En will be degenerate, and that number of total degeneracy can be found in this way. You just recall this thing, that value of M can be from minus L to plus L, spaced by every difference number 1. So that means it comes to twice L plus 1. So that is the thing, and L values is possible from L is equal to 0 to n minus 1. Okay, so principal value L ranges from 0, 1, 2, 3 up to n minus 1. So the possible values of L can ranges from 0 to n minus 1, and for fixed value of L, M can be ranges from minus L to L. That means total number is by mathematics twice L plus 1, and that value is 1. So when L is equal to 0, 2 into 0 plus 1 is 1. When L is equal to 1, 2 into 1 plus 3. So 1 plus 3 plus 5 and so on up to when L is equal to n minus 1, you will get this one. Okay. Now you add it. When you add it, we have this formula that is equal to n squared. That is from your algebra that you must have learned in your plus 2 classes. Okay, that is simple mathematics. Now, you please remember that so far our calculation was non-relativistic, and these are the results that we are getting. That is, principal quantum number can start from 1, 2, 3 and so on. Okay, and azimuthal quantum number or orbital quantum number small l can be 0, 1, 2, 3 up to n minus 1, and magnetic quantum M can be values, possible values is minus L to plus L, integrally spaced values from minus L to plus L. And when you consider this relativistic spin orbit interaction or electron self-energy correction, then that degeneracy will be removed. That means all these states will have different energies. That will that you have to note it. But in our present case, we do not consider these things. Okay, so we consider only non-relativistic case and without any correction of this part. So that is the simplest one. Now I am recalling that equation number 37. This equation 37 is the well-known equation, associated Laguerre equation, and whose solution is this one. Okay, that is Laguerre polynomial, associated Laguerre polynomial expression that we highlighted here, and it is expressed in terms of rho. Now the required solution of this time-independent Schrodinger wave equation, that is your eigenfunction, depends on this value, quantum number small n, L and M. So I have started using it instead of psi, simply subscript by along with the subscript n, L, M, and that we call it radial function depending on the quantum number small n and L, and that y, that was our spherical harmonics that we have seen earlier. Okay, so I am expressing it in this way. Now this should be normalized. So that normalization condition, I am putting it in this mathematical expression. Okay, so one for dr and one for d theta, d phi, that wave function I am putting it mod square, wave function square mod square, that is on the last part. Okay, now I am putting these values of this psi in these values in that equation, and after putting it, that r is taken out. So remaining, this part is for the integral for the r part, from r can be from 0 to infinity, and the other is for the angular part. Okay, this angular part will be equal to 1, that we have known. I have also said it for while solving that angular part equation, that value will be 1 because y element they are orthonormal in a spherical surface, in a unit spherical surface. Okay, so since this value is 1, only I will get this one. So while normalizing, simply you can consider only the radial function. You can forget about this. You can forget this y element function, that spherical part. You can forget it. So again, I am repeating here. That's equation number 42, and the reason that I am again writing here, that it should be normalized in a unit sphere, that spherical harmonic part. Okay, and that is one which you have, this exercise you have already studied in your 5th semester mathematical classes. So simply I am recalling these values, otherwise it will take a lot of time or tedious thing, and for in our present syllabus you can simply put the result because you have studied this thing earlier. So the normalized function after this part also I have skipped only the result I am putting in. On normalization, we find this expression for radial function as this one. Okay, so this will be the required normalized eigenfunction, and here the symbol a nu, this here a nu, this value is 4 pi epsilon I square by mu e square, and this is known as modified Bohr radius. Okay, and that rho, earlier I said alpha times r, that expression again, and when you put in terms of this mu, you get that one expression. Okay, so this is the thing. So with this I end my lectures here.